Good morning, everyone. I hope that your week is rolling along nice and smoothly. We're going to be covering lesson 20.9.1, projectile motion, today. We have another lesson dealing with projectile motion, which we will look at tomorrow, which extends what we learned today a little bit further. And then we are done the unit. Our unit exam is not going to be next week, though, I would assume. We still have at least 2 days of unit review that I would normally schedule in. I would like to spend at least 1, maybe 2 days with you going through some of the material that was covered while I was away, because I'm sure that the questions are piling up. And I would be happy to spend class time going over things with you to help you out. But as well, there will be at least 1 or 2 labs that we're going to be doing next week. We would normally do these labs as we were learning these different lessons, but I haven't been there, so setting up a lab was not an option. So we're looking at page 37 of your unit handout. We're going to be solving today problems involving projectiles. What is a projectile? A projectile is an object that is launched into the air, and these are going to be launched horizontally. So, for example, if I stand on top of a balcony and I throw a tennis ball horizontally from that balcony, it's going to follow some kind of curve, and we're going to use the physics that we've already learned to find out information about the motion of those types of projectiles. This is a bit of a review from yesterday, but I think it's very important. Objects trying to move in a particular direction but experiencing some other influence end up moving in a direction that's, I guess, determined by the direction they want to move in and the direction of the influence. In our examples yesterday, we were talking about boats in rivers, but they could be planes moving through the air. The classic example that we had, and I don't know if the directions are exactly the same as the one we did yesterday, but when we had a boat that was steering north and had an engine speed of 4 meters per second, and the river was flowing west at 3 meters per second, you have to add those two velocities together. The velocity of the boat, which is 4 meters per second, and the velocity of the water, which is 3 meters per second, added together. Well, the velocity of the boat is north, the velocity of the water or river is west. So you add them together by drawing them tip to tail, and that 5 meters per second is what we call the resultant velocity. And I don't care about the angle today, that's not important. But it doesn't change the fact that even though the boat travels at an angle, and I know we talked about this yesterday, or I talked about it yesterday, but it's that important that it bears repeating. It doesn't change the fact that it's still going to travel 4 meters per second north, and it's still going to travel 3 meters per second west. Every second that elapses, the boat will get 4 meters closer to the shore, and every second that elapses, the boat will move 3 meters further downstream. And to put that into words, regardless of how fast the river flows, if the engine speed is constant at 4 meters per second, then the boat will move 4 meters north per second. And regardless of how fast the engine is throttled, if the river is flowing 3 meters per second west, then the boat will travel 3 meters west every second. And this is the most important starting point for today, that the horizontal and vertical components of motion are independent of each other. And yesterday, what that meant is we could use V equals d over t. However, we could only do this if the directions of the two vectors were identical. So I can use horizontal velocity equals horizontal displacement over time, or I can use vertical velocity equals vertical displacement over time. Now, what's going to change today is that in the examples we looked at yesterday, both components were uniform motion. In other words, the river was flowing at a constant velocity, and the boat was attempting to go, in our example, north at a constant velocity. So we have, for the horizontal, we have v equals d over t. This is uniform motion. And this is uniform motion. And that's true for the boat example in the water. What I'm telling you is it will not be true today. All right, let's take a look at the warm-up on the next page. We have a river that is 80 meters wide and it's flowing east at 8 meters per second. We launch a boat from the north shore of the river and it's going to point south and it's going to accelerate from rest uniformly at 10 meters per second squared. So it's accelerating south at 10 meters per second squared from rest. Now I want you to draw a diagram, and I didn't give you adequate space here to draw the diagram. You can draw this diagram at the bottom of the page, even though you're going to be drawing it in the section that has a different question. The answer to that question is going to be very brief, so it won't require a lot of room. I'm just going to draw it on a different page up here. What we're talking about is a river that is flowing east. So, you know, a river isn't perfectly straight like this, but this will give you an idea of what's going on. We have the river flowing east, and it's flowing east at, I want to just check, 8 meters per second. So we can add that to our diagram. The boat starts, I'm just going to draw a dot for the boat and label it as B. The boat starts on the north shore of the river, and the initial velocity of the boat vertically is 0. But we do know that it's going to accelerate. And I'm going to draw the acceleration vector just with a different color than the velocity vector, because these two things are not the same. This acceleration of 10 meters per second squared south, this acceleration is as different to that velocity of 8 meters per second as the color of sky is different to the taste of a cheeseburger. One of these is acceleration, one of these is velocity. I mean, there's another difference as well, and I should include it here. One of the differences as well is that this velocity vector is east, whereas the acceleration vector is south. So that's a picture of what's going on. And obviously, if the river were not flowing, then the boat would travel in a straight line towards the bottom of the page. But that's not what's going to happen. Now we have a clerical correction that needs to be made. I don't know what happened here when I prepared this document. I suspect I was doing some copying and pasting and I forgot to clean it up. But this chart that you have on this page, you're not going to use it. Don't even make reference to it. Don't read it. Don't do anything. You're going to use the single handout, the single page handout that Mr. Gertson has given you. And that's the chart you're going to use. All right, so A asks us to describe the path that the boat actually follows. Well, before we get to that, let's add some information to this chart that I've provided for you. The chart is showing that the motion east is uniform motion, and that's because the river is flowing at a constant speed. And more specifically, we can write what the velocity east of the river is. The velocity is 8 meters per second, and that's east. And I want to make a point to you. That's the velocity of the river east, but since the boat is in the river, that's the east velocity of the boat. The boat, no matter what it does vertically, will be moving horizontally 8 meters per second east. And this does not change. Now, what do we have going on vertically? The motion south is accelerated motion because the engines are accelerating at a rate of 10 meters per second squared south. But I want to add one other thing. That the initial velocity of the boat in the vertical dimension is 0 meters per second. Initially, the boat is not moving south at all. It's accelerating south at a rate of 10 meters per second squared. The acceleration we can put is 10 meters per second squared. Of course, it's south. And we can also add that if the boat goes across the river, it will have a displacement of 80 meters south. And I really want to stress to you that everything in this column of this table is a description vertically in terms of south. And here we can put as a summary as well, the velocity is going to increase. So don't forget, whatever happens horizontally and whatever happens vertically, they happen independent of each other. So these two types of motion, this uniform motion to the east and this uniform acceleration to the south, happen at the same time, but they do not affect each other. Now I want you to take a look at this diagram. And you're not going to, please don't attempt to draw this. If you want, when I get back, I can print out the final result. But this represents the boat initially. It's just sitting there and it's about to leave the shore, and it's moving at that instant in time. It's going to be moving at 8 meters per second to the east because it's in the water. But its initial velocity vertically is nothing. A short period of time later, the boat will be here. I think it's pretty obvious the boat is going to be downstream a little bit. It will still be moving at 8 meters per second east. And I want to point out to everybody that the length of this vector and the length of this vector are the same. It's still moving 8 meters per second east. However, you can see it's now got a velocity towards the south. And if I take a look a short time later, again, it continues to move to the east at the same horizontal velocity. But if you look carefully, the vertical velocity is now greater. And what's going to happen is, because there's an acceleration towards the south, that vertical velocity will continue to increase. And if you just stop and look at what's going on here, the distance horizontally between these images is the same, but the distance vertically between these images is growing. What I mean by that, and again, you're not attempting to draw all of this, is that this distance is the same. It travels equal distances horizontally in equal time intervals. However, when you take a look at the distance traveled here vertically and the distance traveled here vertically and here vertically, these are all increasing. They are all growing. And unlike the boat in the water yesterday, this boat is not traveling in a straight line at an angle. It's traveling in a curvy line at an angle. So this is what the path of the boat will look like. If you want to know the true direction the boat is moving, you can draw all of these perpendicular components tip to tail to get those little itty-bitty hypotenuses. And that means that the boat follows this path. And we can finally answer the question, because that path mathematically is called a parabola. So the answer to this question is the boat follows a parabolic path. And when I say parabolic, and you think of, for those of you that have taken Math 20-1, and you think of the word parabola, that's exactly what I'm talking about. The shape is the same as a parabola. If you have not taken Math 20-1, then you don't need to worry about it. All right, B. How long does it take the boat to reach the south shore? Well, remember, we've set up this table, and what I've got up here is what we've already written in the table. If you want to talk about traveling 80 meters south, which is what it has to do to reach the south shore, then we have to use this information. We have to say, well, it's moving south, so I'm going to talk about its south velocity to begin with. I'm going to talk about its south acceleration. And I'm going to talk about its south displacement. These are all south. So if you want to find the time it takes to travel 80 meters south, then you need to use all of the south components of the motion. Now, I hesitate in putting south here because 0 has no direction, but I just want to highlight that everything is south. And what we're looking at doing now is solving a kinematics equation question. Let's see, I guess I can use D equals VIT plus a half AT squared. VI is 0, so that drops out. I'm left with D equals 1/2 AT squared. I'm going to give everybody here literally just a little less than a minute to put 80 meters in for D, 10 in for A, and solve for T. While you're doing that, I'm going to do it up here. Not so you can copy, but so you can check to make sure you're doing it correctly. I get 4 seconds. So the answer to this question is 4 seconds. Again, I want to stress something here. As long as it starts from rest and accelerates at 10 meters per second squared, it's going to take 4 seconds. It doesn't matter if the river is flowing east at 8 meters per second or at 20 meters per second. It won't matter. And as well, we are asked to determine C, how far downstream will the boat land? Well, how far downstream? That's an east question. What you were asked to find in C is some number of meters, but it's going to be east because downstream will be east. And that means we have to look at what's happening eastwise. What's happening eastwise is uniform motion. And I didn't put any equations in here. On the right-hand side of this table, this is where you have all of those equations. Those 5 kinematics equations that we've talked about. On the left side, well, all we have is speed equals distance over time, or velocity equals displacement over time. So to answer C, all we're going to do is use the velocity equals displacement over time. But since we're trying to find a displacement east, we have to use the velocity east, which was 8 meters per second. East. So I put in the 8 meters per second. I'm trying to find the displacement, and it's 4 seconds. And this is one more point I want to make about this chart that we've made. This time over here in the V equals D over T formula, and this time over here in any of the kinematics formulas, are the same time. Because, I've said this yesterday, I've said it already once today. Even though the horizontal motion and the vertical motion happen independently of each other, they're both happening at the same time. So if it takes the boat 4 seconds to cross the river, then it will have been in the water for 4 seconds moving east for that period of time. So we can now answer this question. Multiplying this out gives the displacement is 32 meters. So the boat is going to land 32 meters east of where it started. And I hope that first example made sense. There's a question at the bottom of the page that we have to talk about, but I just want to summarize this first by saying that the important aspect of this example is you treat the horizontal and vertical analyses differently. You don't refer to the horizontal when you're calculating something vertically, and vice versa. The difference in what we're about to do is rather than having an engine that accelerates something at 10 meters per second squared, we're going to have the acceleration due to gravity accelerating the objects vertically. But it doesn't change the fact that you treat the two types of motion separately. So before we get to the examples, there's this question. 2 ball bearings are released at the same time from the same height, say 2 meters above the floor. Ball bearing A is dropped and ball bearing B is fired at 4 meters per second. Which reaches the ground first? Well, I have a demonstration I would show you, but I can't be there to show you the demonstration. So instead, I'm going to show you a YouTube video. I know that you're watching a YouTube video of this, so this is going to be a YouTube video within a YouTube video demonstrating that an object that is dropped at the exact same time as an object that is fired horizontally will land at the same time. So right now, if you look at the state of this thing, there's a spring that's been compressed, and on the left-hand side of the apparatus, there's a rod. And you were able to put a ball on that rod. The ball is going to have a hole drilled through it. The ball is going to hang on that rod so that if the spring is released, that rod retracts very quickly and the ball falls straight down. On the other hand, on the right-hand side of the apparatus, just below this fellow's forearm, there's a little platform that you can put an identical ball on, and when the spring is released, the metal rod is going to move to the right very quickly, hitting that ball, causing it to move to the right. That's just showing the ball falling straight down. Now he's going to show the ball moving to the right. And now we're going to look at them both at the same time. And they hit the ground at the exact same time. The explanation for that lies in the fact that the reason the ball moves towards the floor is there's a gravitational force acting on it, which causes the object to accelerate towards the floor at 9.81 meters per second squared. And it doesn't matter that one of the balls is moving to the right at the same time, it's still going to accelerate towards the floor at that rate. So which reaches the floor first? They reach at the same time. I hope I've set the stage here so that these examples don't take us a very long time. A small toy car rolls off of the edge of a table at 4 meters per second, and the tabletop is 1.5 meters above the floor. The question is, how far does the toy car travel before it strikes the floor? Well, you are going to set these up, everybody, always in the same way. You're going to make a chart where you can summarize the motion that's going on horizontally and the motion that's going on vertically. So what you have under the horizontal side is uniform motion, which means you use velocity equals displacement over time. Whereas vertically, you have accelerated motion going on. And that means you have all kinds of descriptors. You have VF, VI, A, D, and T. Whereas on the left-hand side, you only have V, D, and T. Now, what is it you're asked to find? How far does the toy car travel horizontally before it reaches the floor? You're asked to find this distance, the distance from here to here. And that's a displacement, but it's horizontally displaced. So looking at your chart, this is our goal. This is what we need to know to answer the question. Well, this is the answer to the question. And if you look at the formula in that column, in order for us to find D, this D I've highlighted is this D right here, then I need to know the horizontal velocity of the car. Well, I think I know that. You're told in the question it's 4 meters per second. So we can actually write that in. But we do not know the time. And when you look at the equation in the x column, speed equals distance over time, we need the time to find the distance. So our problem then becomes, let's go over to the other column and find the time there. The initial velocity vertically of the car is 0 because it's moving horizontally to begin with. We don't know the vertical velocity when it reaches the ground. We do know that A is negative 9.81 meters per second squared. And we do know D. D is negative 1.5 meters. We're talking about a vertical displacement of the car, which is negative 1.5 meters. Listen. You have enough information in the right-hand column to use a kinematics formula to find the time. There's enough information here for us to find the time. But whatever time you get is the time it takes to move that horizontal distance. All right, well, let's calculate the time. I can use the formula under the vertical side of things, D equals a half AT squared, because VI is 0. So we put in negative 1.5. This is equal to 1/2 times negative 9.81, and then times T squared. We grab our calculator. Negative 1.5 times 2 to get rid of the half, divided by negative 9.81 equals that number. We take the square root. The car takes 0.553 seconds to reach the floor. And that means it's moving to the right at 4 meters per second for 0.553 seconds. So now we can use our speed equals distance over time formula. 4 meters per second equals the horizontal distance or displacement traveled times the 0.553 seconds, and get the answer to the question. So about 2.2 meters. Let me show this to you with everything. That chart is key. You set up an X and a Y column. The X is always going to be your uniform motion, which is speed equals distance over time. The Y is always going to be all of your kinematics, accelerated motion information. Since we wanted to find the horizontal displacement but was missing the time, we went over to the other column to find the time vertically, but the time vertically is the time horizontally. Let's take a look at the next question. The next question says, when you solve this problem, we used 2 physics principles from your formula sheet. So you're going to need to be looking at your formula sheet here. Well, what 2 physics principles did we use? We did a time calculation that involved accelerated motion first, and then we did a speed equals distance over time calculation, which used uniform motion second. So the first thing we did was we applied this principle. We did some work in the accelerated motion column, and the second thing we did was this. So the answer to this question is going to be 1, 0. All right, let's try another one. A stunt person drives off of a cliff that is 75 meters above the water. The driver lands 132 meters from the base of the cliff. And then it's asking us what are the physics principles we would use to find the speed that the driver was traveling at. Well, before we do that, maybe let's just set this up to show how we would find the speed that the car was traveling at. What you would do, of course, is you would have your x and your y. Here you're going to have the horizontal velocity of the car before it leaves the cliff, which is what we're after. You're going to have the horizontal displacement, and you're going to have the time. Here you're going to have VI, which is 0 because the car drives off the cliff horizontally. You're going to have VF, which we probably almost never care about. You're going to have the acceleration, which is negative 9.81. You're going to have the displacement, and you're going to have the time. And I'm going to have to go back and look at the numbers in the question. It says the cliff was 75 meters above the water. That means the displacement of the car vertically will be negative 75 meters. And the car hits the water 132 meters from the base of the cliff. That means that d is 132 under x. So how would we go about finding this velocity? Well, that velocity is equal to distance over time, which is 132 meters, over, well, we don't know the time, but we can find the time in the vertical column to put the time in the horizontal column to put it into our equation. And again, we're going to use the d equals 1/2 at squared formula, which you will always be able to do for objects that are launched horizontally. So I'm going to give everybody a minute to calculate the time there. I'm not even going to write down my work in calculating it. You have the displacement of negative 75 and the acceleration of negative 9.81. You need to put them into that formula to find the time. What that's going to look like on a calculator is we're going to take the negative 75 meters, multiply by 2 to get rid of the half, divide by the negative 9.81, take the square root. That's a heck of a ride. The driver is flying through the air for a total of 3.91 seconds. Now that we know the time that it takes to reach the water because of its vertical motion, we know that's the time that it's moving to the right, and we can put that time in here. So if I take 132 meters divided by 3.91 seconds, I'm going to get the answer to the question. About 34 meters per second. Which is a little bit over, probably be about 120 kilometers per hour. If we multiply by 3.6, about 122 kilometers per hour. And by the way, again, just like the first set of examples, we did an accelerated motion calculation followed by a uniform motion calculation. So in answering the first part of this, which is numerical response 3, we would put 1, and then 0. And then, of course, our answer here was 34 meters per second. A ball rolls off of a tabletop that is 175 centimeters above the floor. That means the displacement of the ball vertically, this is all vertical that I'm writing here, would be negative 1.75 meters. We know the acceleration of the ball vertically is negative 9.81 meters per second squared. How long does it take to reach the floor? If it's moving 1 meter per second square, 1 meter per second when it leaves the table, well, look, if it rolls off of the table, that means its initial vertical velocity is 0. Because it's rolling horizontally, I would assume. I would assume the table is level. And that over here is all vertical. This is a horizontal velocity. So you know what? Who cares what that number is? It doesn't matter. To find the time, you're going to use d equals 1/2 at squared. It's not going to matter how fast it was moving. In fact, just to look ahead, whatever we get for an answer here for this part of the question is the same as what we would get for this part of the question. Again, I really believe putting in your d and your a into this equation and rearranging for t is child's play. It's really simple. I will show my work this time. Negative 1.75 equals 1/2 times negative 9.81 times t squared. So to unwrap this for t, what you need to do is take that displacement of negative 1.75, multiply by 2 to get rid of the 1/2, divide by negative 9.81 to get rid of the negative 9.81, and take the square root. So the answer to the question is about 0.60 seconds. And again, the fact that it's moving with a different horizontal speed in part B doesn't change all of this information on the left-hand side of the screen, which means it's still going to be 0.60 seconds. Couple more quick questions. Baseball player throws a ball horizontally to first base. If you haven't clued in on this yet, I hope you do now. This VI equals 0 under the vertical column is because the object is initially moving horizontally. Regardless of what this question is beyond this point, you're still going to say we have under the x column you're still going to say we have V equals, D equals, T equals, and under the Y you have VI, VF, AD, and T. And I admit I'm getting a little lazy here with this example now that I didn't put the vectors in it, but the vectors are included as directions based on which column these things are in. The horizontal distance to first base is 10.6 meters. That's a horizontal distance. The ball drops 1.8 meters. That's a vertical displacement. The acceleration is negative 9.81. We want to find the speed that the ball was thrown at. Well, this is the same as the stunt car question, presented differently. I'm going to give everybody 1 minute to find the time. So to find the time, you're going to use D equals 1/2 AT squared. This is almost exclusively what you're going to be relying on here on the vertical side of things. To find the speed, you're going to use speed equals distance over time. All right. Again, if this is an assignment, you would show all your work, but it's not, so we don't have to. To find the time, I'm going to take that distance of negative 1.8, and I'm going to multiply by 2 and divide by the acceleration. And then take the square root. So this is the time, 0.61 seconds. You can write that down somewhere. You can put it under T. I guess I shouldn't be so lazy. Let me write it down. 0.61 seconds. But that's the time it's in the air horizontally because, again, we analyze vertical and horizontal motion separately, but they're happening at the same time. So that's the time in seconds. To find the speed, we're just going to take the distance, which is 10.6, and divide by that time. So the ball was thrown with a speed of about 17.5 meters per second, or 18 meters per second. I guess we'll go 17.5. One final example. A bullet is fired horizontally with a particular speed at a target that is 300 meters away. If you've ever done any target shooting, you know that you have to aim a little bit higher than your target, particularly over long distances, because the bullet will move through the air at a particular speed, but just like a ball rolling off of a table, it will accelerate towards the surface of the earth. What does this look like? Well, we're going to have X and Y. X is uniform motion, so speed equals distance over time. And the speed is 450 meters per second, and the distance is 300 meters. Under Y, we have vertical acceleration. Since the bullet is fired horizontally, it has no vertical component to its velocity to begin with. The acceleration due to gravity is negative 9.81. You're asked to find how much higher than the target the shooter should aim, so what we need to do is find out how much the bullet falls. And that's it. Well, when you look at the Y column, you only have two quantities, and you should know from our kinematics lessons you need three quantities to find a fourth. The quantity we're going to find is T, and we can find the time on the left-hand column by using speed equals distance over time. So if we solve that little equation, we will get the length of time the bullet is in the air. It's going to be 300 divided by 450, which is 0.6 repeating seconds. That's how long it takes the bullet to travel horizontally 300 meters. So that's also how long it takes the bullet to fall as it reaches the target. And now we can find d. And again, we're going to use the d equals 1/2 at squared. D equals 1/2 the acceleration, negative 9.81, times the time, which is 0.6 repeating squared. And this will give us, well, it's not quite going to give us the answer. Let me calculate it with you first, and then I'll explain why it's not actually the answer to the question. 1/2, which is 0.5, times negative 9.81 times our time squared gives me negative 2.18 meters. The reason why that is not the answer is the answer wasn't what's the displacement of the bullet. The answer was how much higher should the shooter aim. So the shooter should aim 2.18 meters higher. And finally, what two physics principles did we use? Well, if you look at what we did, we used uniform motion first. We calculated that time first in the x column. And uniform motion on your formula sheet is physics principle 0. And then, after we found the time, we did an accelerated motion calculation, and accelerated motion is physics principle 1. You have some questions to practice. What you're going to do for all of these questions is basically take this approach where you have a chart. The chart is going to distinguish between horizontal and vertical motion. Of course, horizontal motion is uniform motion and makes use of speed, distance, and time, or if you like, velocity, displacement, and time. And that means that you use the formula velocity equals displacement over time, the uniform motion formula. With the uniform acceleration, you're making use of all of these quantities. And that means you're making use of a formula like this, or you may encounter a situation in today's assignment where you have to use the VF squared formula. Anyway, your teacher at this point can pause this so you can take a look at it and analyze it. If you want to take a picture of it with your phone, you can certainly do that. In the meantime, we have one more lesson to go. As I said, it will be projectile motion at an angle, and that's going to be tomorrow. I hope that was helpful, and I hope that you have a great day. Take care of yourselves.